Yeah, that's good day.
Yeah, so Tuesday's the Module 2 test, and today is a day of reviewing the module and kind of like doing some review prep for the test itself. I also want to do an experiment, and this one doesn't take very much time to set up, but it'll take a while to actually like run, but it's just kind of one that we can have going in the background. All right, so let's open up to experiment.
Experiment what?
I don't know yet. 2.3. Oh yes, thank you. And I'll collect your, so right now you guys are turning in your lab reports and your on your own questions. You can pass those to Jake. So turn in your lab reports and your on your own questions. Right now you are turning in your lab reports and on your own questions. I don't see everybody moving.
I already turned mine in.
Okay, that's good. I wasn't talking about you, but thank you.
Are we supposed to turn in the study guides too, or no?
Those are due next class. So, but if you have them, you can.
On your own.
When you come to take the test.
Yeah, those are those plus the lab reports that we haven't already turned them in. Yes, Bill.
So my mom told me to ask
you
you a
might need
question
to
to
read
make
it.
it easier. In the actual grade book,
Yeah.
how do we grade our on your own questions?
Oh, good question. Yeah, so how do you grade your on your own questions? So when you go to the end of the
Not in
module.
the grade book?
Yeah, so the solutions book, they mentioned this actually like in the text, I think in module 1 where it said like go to the end of the module to find the on your own questions. But if you didn't see that, it would be confusing because you got an answer key book.
Just look in the grade book.
Yeah.
I'm so dumb. I'm sorry.
So no, that's fine. I mean, that would be logical to do. So because the study guide's answers are in this book, and that's the main reason you guys have this book. The on your own questions are just answered at the end of the module, so they're in the textbook. So, and again, just make sure that if you check your work, make sure it's clear to me that you did everything passed in.
No, probably not.
Oh, yeah, you can get yours going. All right, so experiment 2.3. This one deals with greenhouse gases, and so specifically carbon dioxide. So remind me, what's a greenhouse gas?
Greenhouse.
Mm-hmm.
When the sun's rays hit the earth and when the sun's rays bounce back, the ozone layer catches it.
It's not going to be the ozone layer exactly. I mean, it is true that the ozone layer will catch some, but it's not just the ozone layer.
Well, that, I don't know specifically what layer catches it.
But it'll be ozone and other greenhouse gases, which are in the atmosphere. So very good. Yes, and it'll catch the heat. So yeah, good job. Now, this is again module 2, lesson for 2.3. So if we were doing a lab report on this one, which we're not, then we would put that in our background, defining greenhouse gases. But what about the research question? So our research question is, again, you're not actually doing a lab report on this, but we'll just kind of do one on the board a little bit. Will air with a heightened CO2 concentration or heightened concentration of carbon dioxide trap more heat than normal air. So what we're going to do in this experiment is we're going to have two little plastic bags. And in each plastic bag, we're going to place a thermometer. We're going to just kind of get, and ideally we probably should have had bigger bags than these, but we're going to kind of trap some air in each bag and then leave them out in the sunlight and see how much warmer they get. But the difference between the two bags is that one of them is just going to be normal air and the other one's going to be a mix of normal air and then extra carbon dioxide. And we're going to trap the extra carbon dioxide and then basically like just kind of blow that into this bag. So bag, and I should label these. This will be the bag that has more carbon dioxide. So I'll just write CO2.
I have a question. So, with two bags, should we put the, when we're testing it, should we put it at the same time?
Yes, that's a very good point. So, why would it be a better experiment to actually put both of them, like, side by side out in the sun at the same time? Yeah.
Because then, if the sun comes over the bag, then they both will have the same non-sunlight and sunlight.
Exactly. Because, I mean, think about it this way. If we run the experiment for, 15 minutes, it might be you put the carbon dioxide bag out and for 15 minutes there's cloud cover. And then you put the non-carbon dioxide bag out and for 15 minutes there's direct sunlight. Wouldn't that mess up the experiment? Mm-hmm. Yeah, very good, Sarah. First thing we need to do, I'll put a thermometer in each bag. And what do you think would be a good idea to do before we do anything else? Like before we actually put, I guess we wouldn't have to do it right now, but before we test, is there only one thermometer? I think there might only, oh no, here's the other one. It's like, I could have sworn there were two. I actually have my wife pack all the science supplies for me because she's more reliable with this kind of thing. She's amazing. All right, so anyway, at some point, and probably the best time to do this would be like right before we put them outside. What do you think we should do with the thermometers before we start the experiment?
Cover 'em.
What's that?
Cover 'em.
Not exactly. We want them to get direct sunlight. But one thing actually on that note, we want to make sure that the thermometer, the part that reads the temperature down here, this thing, isn't going to be covered. We want to make sure they're both getting the same amount of light. What else? So we should make sure that the thermometers are both reading the same temperature. Because if they're not, one of the thermometers is kind of skewed as compared to the other one. So in case I forget to do that later, I'm looking at them and they're both saying it is 79 degrees. So that's good. All right. So how do we generate our carbon dioxide? And before we go any farther, let's just make a hypothesis. So we did our research question, and what part of the experiment do we put that under? How do we label that one?
Background?
Not background.
Yeah. Purpose?
First part is the purpose. So purpose with the research question. Then we do the background, which if we were doing a lab report, we would define greenhouse, maybe greenhouse gases and the greenhouse effect. That's what I would define. And then we need a hypothesis. So which bag do you think is going to end up hotter? The one with more carbon dioxide or the one that's just normal air?
Carbon dioxide.
Yeah, that's what I'm expecting to see too. How much hotter do you think it'll be? Like how many degrees? If we were to put the bag out for, we could really choose how long we put it out, but let's say 15 minutes. 5 degrees hotter in 15 minutes? All right. You know what, let's make it 20 minutes. Because we really can choose, there's nothing forcing us to do 15. So that would be like, what, 7.5 then? If we move it at the same ratio. Okay, so now somebody can start reading the instructions, starting with.
I still have it here, but it's fine. This page.
What's that?
Page with the experiment on it.
At this point, we're going to be on page
33.
34. It starts on 33, but.
It's straight through it. You want to read the procedure?
Yeah, starting with part B, running the experiment with carbon dioxide. So take the bag off the windowsill, we don't need to do that. Open the bag, remove the thermometer, don't need to do that. Fill the bottle. Okay, so starting with step 4. And if somebody wants to be the hands in this experiment, you can. All right, and you three, if you come up, I'll let you take turns with this. Because there's little jobs that you can each do. Let's take this one.
Are those the same laws that we used last week?
Mm-hmm. But they've improved. All right, so that, check that bag for me and make sure there's a little hole. I'm holding my breath. Yes. Okay. So somebody will read step 4. One of you can be in charge of the vinegar, the other the baking soda, and the other the bottle in the bag.
Read procedure.
Well, at least you might want to move your book out.
Yeah, and actually we're going to start with the baking soda rather than the vinegar.
That's right.
Alright, so, yeah, let's do step 5 before step 4. I have a reason.
Sure, it's okay if I open this, right?
Yeah.
Okay.
And there might be like a place you can kind of pour out the side. Yeah, there you go.
Thank you.
Alright, so starting with, I guess I can read this, I'm not doing anything. Measure out 1 teaspoon of baking soda and add it to the vinegar. So in this case, what I'd like you to do is, Sarah, you could take the bag and see how there's a corner that's been cut? That's going to be your funnel. So you can kind of open the bag at the top and then hold that cut part so that it's actually like in the bottle a little bit. And Bo, you can take the teaspoon and put it in the bag and shake the bag until the until all the baking soda is in the bottle.
1 teaspoon. Right.
Like take the bottom and
Yeah, Marie, you can help if you need to. And I'm going to move the camera, so this is actually like something we're seeing. Holding my breath again.
Either or, yeah, that way.
Keep my parchment. And I just got baking soda.
Alright, so you got the baking soda in?
Yes.
A little bit, but I'm trying. Chug.
Oh, I thought it was
Now somebody could rinse that bag out real quick. For what Sarah has, because we're going to use it for vinegar now.
Yay.
Don't want the reaction to happen.
Yeah.
I'll put on a show. You cut your hair.
Now, did you cut your hair, or your mom, or did you actually go to like a barber?
I went to an actual place. I did not cut my hair.
We cut Isaac's hair, and he's never had a problem with that until this last haircut. But if you look at his head like closely, you'll see that a lot of his. We're talking about giving Isaac a haircut. There's like, you know, one of his sideburns is like kind of cut off, and the other one's not, and like there's different mismatched places. That's because for some reason he decided he didn't like haircuts anymore. He screamed and thrashed for about an hour. Some of which we were cutting his hair. Other times we were just trying to convince him it wouldn't hurt. And of course we did it, and he said it didn't hurt. But you know, anyway, he has a very uneven haircut as a result. So this will be 1/3 of the way full of vinegar. So you're gonna put a bunch of vinegar in.
Oh, 1/3 of the, how much is
do
that?
we
It's just
need the
slowly
bag?
pour it in there.
Please, you tell me when to stop, okay?
Okay.
I'm not needed.
And one thing that the bag is gonna do is it's gonna make it come in, you know, kind of slowly.
You want to look for the liquid level or the bubble level?
How do you stop it right now? Not right now. 2
I think that's
hours.
probably good enough. Even
not
though
a
it said a third.
third.
Yeah, it's not a third, but let's just leave it there.
Okay.
All right, so now we're gonna take
Do we need
this
this
bag.
bag too?
This is the CO2 bag, and
Can I wash my hands?
go ahead
Wait,
and
Do
catch.
we need this bag?
So we're gonna just kind of put the bottle. I guess I can do this part.
Can I wash my hands?
Yeah. Thanks very much.
Thank you.
So I'm gonna put the bottle in there, and now I'm gonna swish it around. Try to get the reaction to go a little bit more. So the reason that I didn't put more vinegar in was because it lets you do like a smaller bottle in the experiment. I think they said like a 1 liter, I'm not sure. And so as I was noticing, like the ratio of the carbon dioxide and the baking soda, it seemed like it wasn't gonna flare up anymore by adding more vinegar. So I stopped here. All right, so hopefully that's enough vinegar and baking soda, you know, to get the most carbon dioxide out. I'm gonna just give it a couple more puffs, maybe just one, and trust that that's enough, hopefully. Okay, so that's our experiment setup. It's pretty easy, really. And so now I'm going to take that, and I'm going to take this. For this one, maybe a better control approach for this one would be, rather than just having air from the atmosphere, maybe I should actually take air from another bottle. And really, you know, ideally the same bottle, but then that's had other stuff in it. So I'm going to just take a puff of air from this bottle, stick it in here. So there's about the same amount of gas in this bottle as compared to the other one. And of course, since the bottles aren't identical, that's not really like the best, most scientific thing to do. But if they were, it probably would be. All right, so we got our 2 bottles. I'm going to once again check the temperatures, make sure they're both about 79. Now I can see that this one had a little more air than this one, but they both got a good amount of gas in them. And so what does this say? This is, hey, wow, this one's already hotter. Yeah, so it looks like the CO2 is already taking an effect. This one's already like, now it could also be, what would potentially be another reason for this one to be hotter than?
It's been sitting in your hand longer?
Okay, that's one thing. Yep, it's been sitting in my hand longer. So I think maybe.
Reaction.
Yeah. So if this is generating CO2, like, you know, there's probably some heat being generated as well. So the fact that I just like puffed that air directly out. So I'm just going to make a note before we start the experiment that the CO2 bag is already at what is that? 77. And this one is, actually, you know what? Hey, look, they're about the same now. I think it was my hand. Yeah, okay. So they're both 77. All right, they're both 77. So I'll set a timer for 20 minutes, which I think I already have one set for 20 minutes because when I put Isaac to sleep and he doesn't want to go to sleep, I say, I'll set a timer and come and check on you in 20 minutes. And that helps him from having tantrums. So yeah, already 20 minutes. And I'm just going to leave them out on the doorstep area so that it's easy to get them back. Let's see. Could somebody prop the store for me? Thank you, Sarah. Okay, thanks. Okay, so check on that in 20 minutes, see if there's a difference. We covered just about everything from the module last class, but there were several kind of smaller points that we didn't get to. So we'll address them now. Is there anything that you guys found particularly interesting in this module?
I found the experiment with oxygen and pyrogen interesting.
Uh-huh. Yeah, how'd that work out for you? Did you get to watch the video on that, or
Yes.
did it actually, like, could you tell what was happening?
Yeah, I
That's
sort
good.
of. I could make it out after reading the experiment in the book.
Good.
Watching the video a couple times.
Now, if you guys actually miss the experiments, like if you're absent during an experiment, then it's up to your parents whether or not you have to do that experiment. Because I will, under normal circumstances, I'll post a video of it, but it may not be the best video. And all these all these experiments in the book are pretty easy to do at home for the most part. Like, you know, there's some that require things like copper wire and test tubes, so you might have to go to like a hobby store for some of that stuff. But generally speaking, you can just do it all with trash. So, in case you haven't noticed. So I mean, you could do your own experiments at home, but I'll leave it up to your parents whenever you're absent. I'll let them make that call. Another thing though is, like, if you had a bunch of, like, if you had some lower like lab report scores and you wanted to bring them up, then it might help you to do additional ones, you know, as in, like, if you're absent, I don't know, let's say there's 5 lab reports in a semester or something, which I think there's like 6 actually. Let's say there's 6. And let's say your lab report scores, let's say it's the 6th one, and your lab report scores are 0, like you really didn't do well on it, or you didn't turn it in or something. 0, 100, 100, 100, and 100. What's your average lab report score right now? You got 4 hundreds and a 0. So 400 divided by, if you guys, don't know how to do this already, it's very important to know how to calculate your grades, but yes.
80%.
80%, good. Because when you're trying to find your grades, what you're doing is you're doing an average. You're saying out of a total of 5 scores, I have 400 points. So you divide 400 by 5, and that gives you 400%, we'll say. Divided by 5 would be 80%. So you have an 80% average. So then, let's say that you are absent for experiment number 6. And you're like, okay, well, do I want to do this at home, or use the class video and turn in a lab report, or do I just want to be exempt because I was absent? If you're pretty sure you're going to get a high grade on that one, would it be better to do it or not?
Do it.
Yeah, because then, if you do that, then you would end up with, let's say you've got 100 on that one. If you don't do it, you just end up with your 80. Because you have a total of 5 lab reports that you're being graded on. But if you do it, and you get 500% out of 6, then what's 500 divided by 6? So 6 times 8 is 48. So you get like an 83 point something percent. So that helped. All right. Let's talk about some stuff we didn't get to cover. I just started to go into the ozone layer last time. You know what, let's review. Let's review before we get to that stuff. But we'll do it real fast. So this is not from this module, but it's good to know. What do you call the layer of air surrounding a planet? Good. And really you should say like the layer of gases surrounding a planet, I guess. Like the gases surrounding a planet. So in our air, we have a certain amount of moisture content. What do you call the moisture content of air?
Humidity.
Humidity, great. There are 2 kinds of humidity. What are they?
Absolute humidity and relative humidity.
Great. So if I have a certain container, and I ask what is the absolute humidity in that container, then what kind of a measurement would I be getting?
The mass.
Yeah. So maybe like 30 grams of water, or something like that. But if I'm asking for the relative humidity, then what kind of a measurement would I be getting? Percent, very good, yes. So like 60% humidity, which means that the air in this container contains 60% of the maximum water vapor that it could contain at that temperature. So as air gets hotter, does its capacity to hold water increase or decrease? Increase, yeah. The hotter the air is, the more moisture it can contain. So what about the composition of normal air?
Like what it's made of?
Yeah, so what percentages?
78% nitrogen, 21% oxygen,
And 1% of other.
and yeah, 1%.
Good. And most of that 1% other is what?
Carbon dioxide,
water
water
vapor,
vapor,
and another 1% of other.
and something else.
Something called argon, and then variable quantities of different pollutants and things like ozone, sulfur oxides, and nitrogen oxides. So yeah, 0.9% of that one is argon. Carbon dioxide is only 0.03%. That's not very much. It's like 3 parts out of 1,000. So actually out of 10,000, right? Because yeah, so 0.1% would be 1 out of 1,000, because a percent is 1 out of 100. So yeah, that would be 3 out of 10,000 parts is carbon dioxide. Not very much. And of course, do you think that would go up if you were somewhere where there had just been a forest fire?
Yeah.
Probably, yeah. There'd be other things in the air if there's a big forest fire, and one of those things would be an increased level of carbon dioxide. Okay, why is it important that most of what we breathe is nitrogen?
Because it doesn't affect us.
Yes, it doesn't affect us. It doesn't really have much of an effect. Did you know that you can actually smell nitrogen in some situations? You know that smell that you, like the kind of the after the rain smell when there's been a lightning storm?
Yeah.
That's burnt nitrogen. So I think it's a really nice smell. Yeah, that's when the lightning burns the nitrogens when you smell that. Okay, and what about when we breathe air? How much oxygen do we take out? And well, what's the composition of the air that we exhale? Let's just say it that way.
16% oxygen, 75% nitrogen,
4% carbon
and
dioxide,
then
4% water vapor, and 4% other.
So 4%, I'll say H2O, 4% CO2. So we add a lot compared to what we take in. And you say 75% nitrogen?
75% nitrogen.
Good. So it pretty much just goes in and out. Am I missing anything?
And 1% of other.
1% other, thanks. That's not very proportional, but whatever. All right. Yeah, so out of out of the 21% oxygen, we use about 1/5 of it to breathe, less than 1/5. I guess well, let's see. We use yeah, just a little under 1/5 of the oxygen that's in the air when we breathe. What are some reasons why you don't want more oxygen in the air?
There's too much oxygen, it can damage your lungs.
Yeah, it can damage, and like if you're a newborn baby, it can damage your vision, things like that. So, out of curiosity, how many of you knew who Stevie Wonder was? Hey, well, I'm impressed. Okay, I figured it would be like nobody, but.
I really know him because at the farm that I work at, they named their cat who has no eyes Stevie Wonder.
Nice.
And they had to explain it to me.
But yeah, of course the parents all knew who Stevie Wonder was, so.
My mom told me that I don't understand.
But anyway, and we've already talked a little bit about the greenhouse effect, so greenhouse effect is going to be the process by which these greenhouse gases trap heat from the sun in the atmosphere. So if we didn't have the greenhouse effect, in other words, if we didn't have as much greenhouse gases, then what would the state of the Earth be like?
Non-life supporting.
Exactly, it'd be too cold. But if you have too much of the greenhouse effect, then what
It'd be
happens?
very hot.
Yeah.
Global warming.
Yeah, if you got too much, then it's global warming. If there's so much of the greenhouse effect that the average temperature of Earth increases, then you call that global warming. So what were some things that he said about global warming?
It was hotter in the Middle Ages than it is now.
Yeah. I think it was in the 50s, but there was a lot of like hype about a second ice age. Like people were afraid of global cooling at that point. But yeah, it was hotter in the Middle Ages. What else? Mm-hmm.
It takes longer for it to occur, for like global warming to occur.
Yeah. So it's interesting because if you see the graph, like you know, the amount of actual temperature change is like, it looks pretty bad because you see it like going up and you're like, oh no, it's going up, and it seems to be going up faster. But what's the scale? These are like 0.2 degrees Celsius in between each of these things. So since you know, about 1900 to 2000, you know, the carbon dioxide has increased from, you know, 280 parts per million to 380, but the temperature increase over that time has not been steady. That's this one down here, and it's also only gone up an average from like basically a range of, if we start from here, let's see, that'd be so 0.8 degrees Celsius total. So it's also interesting because he said that like, while there may be parts of the North Pole where like the ice caps are melting, what did he say about other regions even in the North Pole?
The ice is thickening.
Yeah, the ice is thickening. So in some places there's localized cooling, and in other places there's localized heating. What percentage of you know, what percentage of carbon dioxide in the atmosphere are humans responsible for?
A small percent.
I can't remember what it was though.
It was small.
It was less than 3.
It seemed like about 3%
Yeah,
was what I
approximately
remembered.
3%.
I could be wrong about that, but I think it was 3. And if you remember 3, then yeah. And if you do too. So, and I don't know if that means like we should just totally throw caution to the wind or anything like that, you know, but it is interesting to think about, you know, just the fact that like there hasn't been too dramatic of a change in average temperatures, and then like, you know, the part that we play is about 3%. So anyway, they also talk a little bit about, oh, and I'll just point this out because he points it out. What was his point about the chart here, like the graph there, as compared to the one here? Yeah.
The other one, like the range is just within 0, like goes up to like 0.9 or something. I think. Versus that other one, it's ranged up to like a much larger number.
Yeah. So this one is like 10 times the range because the other one was like 0.8 to 0.6. This one is like 8 to 6, so 10 times as much.
So it's like the other one zoomed in, so it's really not that much bigger.
Yeah. So you can, if you ever want to scare somebody with data, zoom in your graph because then it'll make any change look huge, even if it was a very small change. So honestly, I think that like, you know, my 2 majors in college were English and political science, and in political science they make you take a statistics class, and there's a lot of statistics that pop up in other classes. What is statistics as a math? It's a branch of math, but what does it cover?
It's like
Percentages.
Percentages.
graphs and percentages and like
Mm-hmm.
data.
Yeah, data. So what's that?
Probability.
Yeah, probability would be included. Good. Yeah, so statistics is basically where you're going to be like compiling and representing and analyzing numerical data. And so Mark Twain famously said, and I'm going to make his quote G-rated rather than the original, but he said there are 3 kinds of lies: lies, darned lies, and statistics. And his point was that basically you can use numbers even in statistics, which would seem really reliable, but you can even use them to deceive people if you present them in certain ways. And so I think one of the best ways not to be deceived is to study a little bit of statistics, because you'll find out, like, you know, you see this chart and it's like this, and you're like, oh my gosh, that looks terrible. Look how much hotter look how much global warming has happened. And then you look really carefully, if you're trained in statistics or whatever, you look over here and you might see like, you know, it's 0.005 degrees, and this one's like, you know, 0.006 degrees, and you're like, wait a second, that's barely going up at all. You know, it's because it's zoomed in really, really far that it looks scary. So that's just one example of statistics. And statistics could be deceptive even if it's not on a graph. Like, I'll just give you one example. There was a time when there was a particular political official under investigation, and this would be an official that like some news programs would be favorable toward and others would be opposed to. And one news program says that he's been required to submit like thousands of documents that he still hasn't submitted about this case that he was under, and then the other news program says basically like, this man has submitted thousands and thousands of documents, but they're still requiring thousands more from him. Which one is more favorable toward the guy? Yeah, the second one. So it's like this poor man. They're asking so much of him, and but then the other one's just like pointing out like, no, he's not giving all the information he's being required to. So it's kind of interesting. That would just be another example. You're using numbers, just like thousands of documents or whatever, but even without a graph, you could put a spin on numbers. All right. So we will move on. And while I'm on things like that, let's talk about a cost-benefit analysis. I'm going out of order now. But what is a cost-benefit analysis?
It's like the ratio of like the cost, the benefit, like is it actually worth it?
Yeah, is it actually worth it? So let's take a situation where you might create a cost-benefit analysis. What's a decision you might make that could require like a cost-benefit analysis? You do a small cost-benefit analysis every time you buy lunch. You ask yourself, is the benefit of this food better? Is that does that outweigh the cost of paying for it? So give me another situation.
Buying a new house.
Okay, yeah, that's definitely good. So buying a new house. That one is one that you would have a lot of cost-benefit analysis going on, probably. So let's name some costs and some benefits of a particular house. I never made a list, but I definitely did this when we bought our house. So
some costs could be like, first of all, having to like buy it, and then also having to like pay for like plumbing and all that.
The process of buying is one thing. It takes a lot of time to buy a house. So I'll say that's a lot of energy. It's also a lot of time.
Whether or not there's anything you need to fix.
Yeah, good.
Like renovation.
Yeah, so repair/renovation costs. Yeah, closing costs. Those will sometimes come up and bite you.
Moving bills?
Oh yeah, definitely. Moving costs.
Would bills differentiate between houses? Like,
Oh yeah, so
electricity?
yeah, so what are the utilities like? I think I'm skipping one. Utilities that you're gonna have to pay for the house, like every month there's electric, water, etc.
That could be a benefit too, because it could go down.
Oh yeah, that's very true. So all these could end up being benefits if you're saving. I'll say homeowners association. Sometimes you have to. Well, I guess everybody probably has to pay them fees. Ours are really steep, but they actually do a lot of good services for us, so I'm okay with it. But we have to pay I think like $700 a year or something to our homeowners association. But they do all of our lawn care on a weekly basis, which is awesome. So it's not so bad.
You're hacking the system with all the bank accounts you have.
Yeah. Those of you who were in my algebra class last year. All right, so homeowners association, lots of different things. I'll say another thing that, this could be on either. Like all of these could be on either because you might be saving money or you might be spending more than your current situation. But definitely your monthly mortgage payment. And if you guys don't really know what that is, that's okay. You're young still. Oh, time to check on the experiment. I'll bring it right back in, and we will record the temperatures. So, yeah, thank you.
I always get colder because all the air is getting sucked out.
Okay. So, the regular air is 109 degrees.
What?
Not exactly.
It was indirect sun.
Oops.
Does not go up to 5 degrees?
Fahrenheit. Gotta have your units. It's already cooling down. Shoot, that's not good. This one was. Oh, that's not good because they're already cooling down. I'll just see what they are right now because they're cooling at a steady rate. So right now that's 101 and 105.
So then couldn't we just add 8 degrees to the other one? And then we could get the original temperature?
Why 8?
Because
Oh, I see what you're saying.
that
Yeah.
one
Yeah,
looks
good idea.
interesting.
Very good idea. Okay. Now, of course, that would be if it's. Yeah, I think that would work. Probably.
We get 7.5 and
Yeah.
Yeah,
This
go
one
get
was.
mine.
What were the numbers I just said? Because it's decreasing.
101.
101 and 103.
All right. So that means that it was probably then about 109 and
112.
yeah. So the regular dropped from there to and then the CO2 one. What was the number I just erased? 105?
105.
All right, 105. Yeah, so when I first saw it, it looked more like about 113. Curious how much it's dropped by now. So now we're at, the regular is at 91, and the other one's at like 94. So, or something like that. Yeah, okay. So it worked. And then if we were actually doing a full lab report, then where would you record this information? What section?
Results.
Results, good. Where would you explain why you think it happened the way it did? Yeah, good. And then in the discussion, you're also going to include whether or not what?
Your hypothesis.
Good. And then in the conclusion section, what are we going to address?
Errors, possible errors, and
Yep.
possible improvements that we can make.
Yeah, so in the conclusion, you'll kind of just say, like, whether or not you fulfilled your goal of, like, for the experiment. Basically, did you answer your research question in a satisfactory way, and were there any errors or ways to improve the experiment? If your answer is no, there were no errors and there are no ways to improve it, then what do you do?
No, there's no error.
Yeah, you tell me that. Because if you don't tell me that, I'll assume you forgot. But if you do tell me that, I'll give you full credit. So, all right. Now, they talk a lot about different pollutants. I already talked about ozone a little bit. And so remember, ozone is an O3 molecule. And if it's at the ground level, where you can actually breathe it, like where you're breathing it, it's bad for you. It's toxic. But if it's not at the ground level, if it's up in the ozone layer of the atmosphere, what does it do that's helpful?
It reflects the ultraviolet rays.
Very good. Yeah, so, and I already talked about that a little bit, but imagine your O3 molecule, and this time I'll draw it more accurately than I did last time. Before I drew them all together like if you were playing pool, like 3 pool balls together. And UV rays are high energy particles. I guess I'll just kind of draw it like that. And they're pure energy. Light is actually pure energy, but in fact it has no mass. And when it strikes, then that energy is going to split apart the ozone actually into like an O1 and an O2, 2 separate, one just an atom, the other one a molecule. And the ozone is actually going to absorb, in doing that, like all the energy from the UV light. So it causes it to go away. Now, they talk a lot about different pollutants at the end. And so what happens what's the pollutant that results if you burn sulfur? Sulfur. Okay, if you burn sulfur, what kind of pollutant gets generated?
carbon monoxide. No, sulfur.
Sulfur.
Yeah, sulfur oxide's good. How do you get carbon monoxide, by the way? Yeah, so it'll be generated in cars. But there's a particular environmental circumstance that will cause carbon monoxide to form.
Isn't it when the gas gasoline gets burned so much that like the something can't keep up.
Yeah, so I think it's,
Oxygen-
isn't it that there's not enough
Okay.
oxygen?
Yeah,
right?
oxygen can't get to it fast enough. and
Yeah.
So then it like backfires or something, and then carbon monoxide.
Very good. What do you call the type of combustion where there's not enough oxygen and carbon monoxide is the byproduct, is the carbon dioxide? Didn't they say that was incomplete combustion?
Yeah.
That sounds familiar to me. So yeah, I'll just kind of list some things. Carbon monoxide. If you were to guess, by the way, so carbon dioxide is CO2. What do you think carbon monoxide would be?
CO.
Yeah, just CO1, or you would only have to say CO. Because di means two, mono means one. So that'll be from incomplete combustion. We have sulfur dioxides. Or sorry, sulfur, was it oxides? Yeah. That'll be from burning sulfur. And they point out that pretty much everything has some sulfur in it. Like if you burn coal, you burn wood, whatever, there's going to be some sulfur in it. And how do you limit this pollutant in like a factory?
That's
Scrubbers. Yep. And then we have nitrogen oxides from burning what? You can probably guess. Yep. Are there any I'm forgetting? Maybe not. Okay, we just got a couple minutes left, a few minutes left. Yeah, so, and I cut our cost-benefit analysis a little bit short, by the way, but the end part would just be if you take a list of the costs and a list of the benefits and you weigh them and see which one is better. All right. Now, yeah, we hit that, got that. Now, in general, have pollutants increased or decreased since 1975? Yeah, we've done a good job of that. And one thing that they did the cost-benefit analysis on was CAFE standards, C-A-F-E, which was corporate average fuel economy standards. And that'll be reducing CO2 in cars. Okay, so things to know for the exam, or for the test, yeah. Okay, your excuse, thanks. So the vocabulary that you will fill in the blank with will be humidity, absolute humidity, relative humidity, greenhouse effect, parts per million. Oh, what does parts per million mean?
It's like the amount of molecules and atoms like within a mixture or substance.
Mm-hmm. And it'll be measured as out of not percent, but out of parts per million. So percent, actually, it's kind of an abbreviation of per, which is Latin for like through, I guess, centum. So it's basically saying out of 100. A percent, Bo, I might have to move you in the future. So percent is parts per 100, but then if you have parts per million, it works exactly like percent, except you know, you're dealing with, instead of out of 100, you're dealing with out of a million. You could convert from percent to parts per million, in fact. So again, it's just the underlined words that they define separate, like where they set them apart, underline them and define them, that are going to be the ones that you fill in. All right. When does water evaporate more slowly, under conditions of high humidity or low humidity? Yeah, so these are things to know for the test. Will sweating help cool you down when the humidity is 100%? No, because it's not going to evaporate, so it's not really going to cool you down. Know that nitrogen makes up most of the air we intake. Know that when we inhale, or when we exhale, it's still mostly what that we're exhaling? Nitrogen, yeah. We're exhaling a little bit more CO2 and a little bit less oxygen and also more water vapor, but we are still mostly inhaling and exhaling nitrogen. know that combustion is going to occur better. Things are going to burn faster and stuff like that with more oxygen. Things would burn out. They would burn out more, quickly if they don't have oxygen because they're not being fueled. But things are going to actually like burn brighter, etc. with oxygen.
So with the vocabulary words, are you gonna do it last time
Yeah, it'll be the same. But this time I actually remembered to cross out the test. The section where they ask you to write out the definitions. I crossed it out, so you just flip the page over, and it'll have the definitions, and you write in the word. So, which I realize is really easy, but whatever. All right. Why is it important to have the ozone layer? We already talked about that, but make sure you understand that. And know that ground level ozone is bad for you, while atmospheric ozone is good for you. Know about whether or not in the last 80 years the average temperature of the Earth has significantly changed. Now you will have a math problem. You have to convert something from percent to parts per million. I'll just finish this up real quick because I'm almost done. So make sure you can convert from percents to parts per million. If you did badly on the unit conversions last time, try to teach yourself how to do unit conversions and be able to do parts per million conversions. The concentration of nitrogen oxides, so that's the second one. They're going to give you the concentration of nitrogen oxides in parts per million. You have to convert back to percent. So be able to go both ways. There's two problems, I think, on that, with percent to parts per million. And finally, know what catalytic converters we're supposed to, what type of pollutant they're supposed to fight. Okay? Everyone good? All right. Take care. Have a good weekend. Hey, it's Labor Day, isn't it? Right? All right. Have a good Labor Day weekend.